We start again, and this will be the last talk in the area of probability and statistics, and I'll try to compress just the highlights, and I'll try to bring them up here. Something you've got to remember, as we see in the slides, is we've been discussing conditional probability, and we've been saying how to get PA given B. And that turns out to be PA times B divided by PB. That turns out to be PA given B. I can actually use this rule which is given by Bayes. Bayes was a priest. This gentleman, he was also a mathematician, and over 100 years ago he came up with this idea of going from P A given B to P B given A, and that's a very simple straightforward application of a little bit of algebra. And let me show you what his formula looks like. Notice here on the left hand side I've got P B given A, which is equal to, by definition of conditional probability, PAB divided by PA. Now I can break up that PAB as PA given B multiplied by PB, and of course, it's just the numerator, and in the denominator I've got the old stuff preserved there. So now on the left hand side I have PB given A, on the right hand side I've got PA given B. So if I know PA given B, and if I know PB and PA, I can compute PB given A. This is a very, very useful relationship. It's called the Bayes rule, and it's by far one of the more powerful results in probability theory. Let me give you one example. I'm not going to be working this example in great detail, but I'm going to give you a hint as to how to work this example. It's the chance that you walk out and you find the grass is wet. Could it have been caused by rain, or was it the sprinkler that was on maybe an hour back or something, so the grass is wet? And based on that, you may decide to carry the umbrella or not to carry the umbrella because the grass is wet. The grass is wet when you find in the morning the grass is wet. You do not necessarily look at the sky. You're rushing, you're going out in your car, so you grab the umbrella and run. So should you or should you not grab that umbrella? That's the question. And there this Bayes rule can be used, and so on and so forth. Couple of things I'd like to make sure you understand is you'll run into terms like prior and probability posterior. Prior is, which is like probability of there being what we call the hypothesis or the evidence, and the evidence is E, hypothesis is H. Let me try to see if I could give you another version of the same. We did the medical test, of course, you remember, there we used the same formula. And the Bayes formula can also be used in more complex situations. Let's get to the point when we got that rain situation again, rain, wet grass and umbrella. And let's take a look at what the problem is that we'd like to tackle. There are three possibilities. One, it has rained or not. I carry the umbrella or I do not carry the umbrella. The grass is wet or it is not wet. So there are three events, and they are actually influenced by each other. And what is given to us is there are certain relationships that are independent. I'm just going to leave this with you. I'm not going to solve this problem. R is the event that it rains. W is the event that grass is wet. U is the event that people carry umbrella with them. And then some conditional probabilities are given as two tables here. Those conditional probabilities are given here. And the question that is being asked is, if these are the conditional probabilities given, will you or will you not bring an umbrella with you that day? And to solve this, what I've done is I've basically worked out the thing, and I'm going to displaying this with a couple of minutes. So I'm going to show you first what this situation is. I am going to be indicating to you two results that we'll be using. One result is this one. Probability of you're carrying the umbrella and grass is wet given that it has rained. If U and W are independent, this can be verified, of course, we can verify that later on. If these are independent, I can break this up into this probability of U given R multiplied by probability of W given R. U is the event that I'm carrying an umbrella, and W is the event that the grass is wet. If these two are independent, I can write it like this. And I can write the same thing for the non-rain situation. This is the situation with rain, this is the situation without rain. And then again I can write this formula. These are given to you. These are provided to you. So we assume them to be true. Then I am given this conditional probability and also this conditional probability. Will I really carry umbrella that day? So to do this, what I do, I bring my solution and I'll just basically let you have a look at the solution. I've worked out the steps here and I've worked out some of the numericals also. So I've calculated here, for example, P, U, R, U and W given R. That is like you carry the umbrella and the grass is wet, given that there is rain. What is the chance for that? I broke that up and I had these quantities from the table. From the matrix table, I had these two quantities. So I plugged those in and I got my probability there. One is this probability, the other is the other probability. Then of course I also worked out the total probability of there being grass being wet, which could happen because of rain or even because of no rain, because the sprinkler comes on when there is no rain. And that probability also I work out. Therefore, from this I can find out the probability of the grass being dry. That probability I work out. And then of course I try to work out the probability of our interest, which is like probability of carrying umbrella given that the grass is wet. And that turns out to be about 95%. I'm going to leave this with you. I'm not going to solve this problem in detail, but you are supposed to work this through and you're supposed to check out the numbers which are there. And you can let me know if the numbers are not correct. So this is like something that we'd like to be able to do. And this is possible when you have your the Bayes rule in effect. Just doing a quick recap of what we've done so far in the area of probability. Mind you, we've not used real data, so we've not really delved into statistics yet. We've just been playing with probability, various principles of probability. What are some of those principles? First of all, we have this notion of population, which is the total extent of the area of interest in which you've got some interest. It could be the total quantity of production done last year or last month or this week. That is the total population. From that I collect a sample, so I've got the idea of sample. I have that. Then I gave you a brief definition of probability. Then of course I gave you a subjective notion of probability and a more objective notion of probability. The subjective notion comes from belief in probability. The belief that on July 15th it's going to rain in Kharagpur. That's a matter of belief. Frequency distribution, of course, will go back into real data. So you'll look at real meteorological data, and from that it will try to figure out how often on July 15th has it rained in Kharagpur. Then we discussed simple events and we discussed compound events, and we looked at conditional probabilities, and we looked at complementary events. We looked at the additive law, and we looked at the multiplicative law. That also we looked at. We looked at independent events. We looked at mutually exclusive events. These we looked at. Then of course I gave you some hint of how data is measured, and this is what we'll be getting into a little bit, not a great deal, but we'll be getting into a little bit into this measure of central tendency and the measure of dispersion. That's what we'll be doing there. There are various types of probabilities, as I indicated, they are available. The moment you start talking about distribution, you're talking about data. You're talking about, if I collect a large volume of data, large amount of data, what kind of distributions will I end up with? That is something that we got to keep in mind, and that will be using when I go into higher level of theory. For example, there is a certain thing called the hypergeometric distribution. Let me give you an idea of that. I have a jar, and I'm going to be drawing it here. I have a jar, and the jar contains some red balls and some black balls. Let's say this jar is our total production. The red ones are the defective items and the black ones are the okay items. Now, this being too large, this quantity being too large, I'm not able to really sample everything. I'm not really being able to test everything. So what I do is, I pull out a sample, and the sample comes out. In here, before I took the sample out, there were there were R red balls and B black balls inside, and R plus B, this is equal to N. That's the total number of balls in the system there. And when I bring out a sample, the sample comes out of this. I have a sample of size N. It has got in that case B black balls and R red balls. That's in the sample. The sample is just a part of it. So just that is the sample. That is what I pulled out. What I'd like to work out is what is the probability of there being B black balls in a sample of N. So the question that I'm asking is the following: probability of there being B black balls in N balls pulled out of the thing. This is the probability that I would like to write down. And let me show you how this probability can be written down. It's not very difficult. Look at the situation. I have a total of R plus B balls, which is like a total of N balls. And out of N balls, I picked little n balls. So really, in terms of combination, these are the different ways I could pick n balls out of big N balls. That is the count of total number of ways by which I could pull out n little n balls out of the total jar. The jar consists of n big balls. Now, the black balls would have come out, black balls in the sample would have come out of these black balls. So I have here B and B. And the red balls would have come out now of the remaining balls, which is N minus B. So I'm going to put N minus B in red color. N minus B. That many red balls are now, that is equal to R actually. This is equal to N minus B. That's what I've got there. And then how many red balls are there now? They are little n minus B. This is the formula that tells you what is the chance of my finding exactly little b black balls in n balls picked in as a sample out of this thing. This distribution is very important in quality assurance when you are sampling from a finite jar, finite population. It could be a basket, it could be a box, it could be a certain number of items that have been placed on your table and you are sampling a few out of them. And this particular distribution has a name. It is called the hypergeometric distribution. It is the hypergeometric distribution. It's a very important distribution in sampling theory. Suppose this jar was very big. And the jar being big would mean that I can only talk in terms of fraction defective. I cannot really count the balls and say how many red balls are there, how many black balls are there. And in that case, I'll be talking in terms of fraction defective, which I could probably denote by a quantity P. P is the fraction defective, fraction of red balls in this full jar there. So really speaking, this P is equal to R divided by N. That's what this is. If this is the story, and I again take out N balls, what is the chance? What is the chance that I have picked so many red balls out of the jar or so many black balls out of the jar? In this case, let's assume that the red balls are the defective ones. So what is this formula now? I will just say this, probability P, that there are, I have picked a total of little n, so I'll really call it here R red balls in N, that is the sample. I sampled N balls, out of them R turned out to be defective. This can be written as following: n choose r, p raised to the power r, 1 minus p raised to the power n minus r. That is the formula that is to be utilized if you want to find out the number of the probability of there being r defective balls in n that you pulled out. I'm calling the red balls now this time to be defective. This is the formula. What is this formula? Where is this from? This is from the binomial distribution. So this is the binomial distribution. This is also a very important distribution like the hypergeometric distribution in probability theory. What is the difference between these two? This applies when your sample size is, when your jar is of finite size. It can all be put on the table, for example. And this formula applies, the binomial formula applies when production quantity is very, very large. And this is generally true when you've got a full truck and you're sampling a few items. So when you look at sampling plans are either based on this or they are based on this. Most of the sampling plans that are used in industry, they are based on the binomial formula. They are based on this. So I just wanted to give you an idea of what it would be if I were doing this, Now, suppose this P was quite small. P was very, very small. That means most of your items were okay. What sort of formula will you use? You'll be using the Poisson formula. And the Poisson formula is listed here. See that Poisson? This again I'm going to show you in a little place. In a little while I'm going to show you where did the formula come from. So let's move on to that. Some basic ideas are shown in the beginning and you get an idea of mu. Mu is the average, mu is the mean, and there's a way to calculate mean. The formula is given there. And there's a way to calculate mean when the situation is discrete. That also is given there. And here's the situation. Let me show you what is happening here. This is fishing of a particular type of fish. Fishing for a particular type of fish in California. And the fishing season starts in summer, toward the end of summer, like July. And then as people start fishing, what you find is this is the length of the fish caught. This side is the length of the fish caught. So if you're more on this side, you've caught large fish. If you're more on this side, you've caught small fish. So probably when the fish are spawning, most of the fish are small. Many are small. They slowly grow and they grow to larger size. And because there are many people who are excited fishing, they go and catch a lot of fish. This is the distribution of fish caught in July. This is like after about mid-July, it's sort of like this. Then later on, in some more time, it moves up like this. Then it moves up like this. In September, it's like this. October, it's like this. And about November, the distribution of the length of the fish, which is like the length between the tail and the head, that moves up to this side. So what is happening here? I'm seeing a shift in the population of the fish that is there. The distribution itself is shifting. There are a couple of things shifting here. One, notice that the mean is shifting. This is a very important thing to notice. The mean length is shifting. And certainly the max is shifting, the min is shifting, but certainly the central tendency of the distribution of the fish caught, that is moving up. And also the variance is changing. Here the variance was wide, so you had a lot of dispersion in this area, and here it has become tight. So actually you have more fish, more or less of the mean size. Not many that are really small, not many that are really big. Around here you had that issue. You had that issue there, but they all seem to grow up into adults and they are like this. This is like, it just gives you an idea. It just gives you an idea of the higher likelihood of catching a big fish as time goes on. If you go and fish in November, you're more likely to catch a big fish. And if you fish in July, you're more likely to catch a small fish. And this has happened because of the shift in the distribution. And of course, growth and the amount of fishing that is going on and so on, all those things would influence this. Let's take a look at some of the measures now. Clearly, the expectation, which is the average of the average size of the random variable, that turns out to be x times PR. In the discrete case and the continuous case, it turns out to be this formula. And I'm pretty sure you're familiar with this. if I have two variables, x1 and x2, and if I want to look at the sum of those random variables, if I want to look at their average value or their expected value, that turns out to be ex1 plus ex2. Nothing very fancy. And of course, you can have many different examples and so on. And all you have to do in this case is you have to figure out these px and py. If you have the px and py known to you, px1, px2 and so on, you can easily calculate the expected value of any of this thing, any of these things. Then there is this measure called variance, and of course I have plotted here this sample variance. Sample variance has a degree of freedom which is like less than the total number of items there, is less by 1, because I have used the data once already. I have calculated x bar, only then I can calculate this variance. When I am calculating sample variance, I lose 1 degree of freedom. So this guy, it turns out to have 1 less degree of freedom as compared to the original number of data points there. And you see the formula for standard deviation of which is just the square root of what we had before. That's what we have here. Then there is a very important quantity called the range. Range is actually a very important quantity. Range also gives you an idea of the dispersion of the data. And range is actually a very simple value to calculate as opposed to this formula here. This is a gigantic formula. It takes a lot of effort to do it unless you're using Excel. If you're using range, all you have to do is look at the largest number in your sample and look at the smallest number in your sample. The difference between those two turns out to be the range of the data values there. And of course, again, I've got the formula for the average there. That can be found. And there is some example there where again you can see this is rho is really the density here, and the density is of two different groups. Those are plotted here and they give you an idea of the standard deviation. So that's also shown here. That's also something that is shown here. It turns out variance is a very good indication of the spread of the data, of the dispersion of the data, and so is range. These are all very, very important. And the formulas, they are shown here. They can be found from any textbook. You of course will not use directly these formulas. You'll be using either a function or built-in software or something to be able to do it. But you must have the concept. You must really understand what it really means. A sample is only, of course, a subset. A sample is not the full population, it's only a subset. So therefore, anything that I calculate from that sample will be qualified by calling it a sample average or a sample variance or a sample standard deviation. This is very, very important. And any quantity that I compute from sample values, those quantities are called statistics. And there is another measure of variation that is called the coefficient of variation, which is just basically the division of sigma divided by mu. That turns out to be the coefficient of variation. And my old professor Jim Templeton, he used to say cats have low CV and dogs have high CV. The reason is this: when you work out this ratio for dogs actually come in widely varying sizes, from little teeny weeny ones that you can carry in your pocket to the big guys. Dogs come in all sizes, therefore dogs sigma is quite a bit high. When you divide that by this, the coefficient of variation for dogs turns out to be high. Cats, on the other hand, they all come more or less of the same size. All cats are about this size. So their standard deviation also is quite small, and their CV then turns out to be also low. So cats have low CV and dogs have large CV, coefficient of variation. Sampling distributions, any data that you calculate using samples, those would be called sample distributions. Let me give you an example. See, remember we sampled from the diagram here. I sampled out of a jar. The jar was of a finer size, and in this case, I turned out to get this into converted into hypergeometric distribution. This probability formula here is based on the hypergeometric distribution. If the jar becomes really large, then of course I have the binomial distribution. So this is also another sampling distribution. This is a sampling distribution which describes the property of the sample, and the binomial distribution also describes the property of a sample. So this also turns out to be a sampling distribution. And this is what we have on the screen here. I have various types of sampling distributions. I'll give you some example. It turns out that there is a theorem called the central limit theorem. It's a very, very powerful and a very useful theorem. What it says is, if you calculate the sum of, it does not matter what kind of random variables, if you calculate their sum, that sum will approach a normal distribution. The sample average or the sum, both of them, they will approach the normal distribution. This is a very useful result. The reason is this: I have many tables available for normal distribution. I've got all kinds of calculations done already by experts who came before us. They've given us tables for the normal distribution. And what this theorem is saying, what central limit theorem is saying is, if you take sums or if you take averages of sample data, the average or the sum, they will approach the normal distribution. And then you can use the normal distribution theory to do any calculation that you want to do. So it's a very, very useful result. If you have Z, now remember Z has been adjusted. X1, X2, X3, they had normal distribution, and Z had the mean subtracted from it divided by the standard deviation. Subtracting the mean shifts the mean to 0, shift the mean. So it turns out that the mean of the quantity Z will have a 0 mean. The mean of this will be 0, and the standard deviation of Z is going to be 1 by the scaling that I have done. If I take these quantities, if I take many of them, if I square them, if I square Z1, so I've got Z1 square plus Z2 square and so on, up to Zn square. I've got n items in the sample. I convert all of those x1, x2 values into Z values. Then I square them, and if I add them, I construct a new summary of the sample statistic. This summary is called the chi-square random variable. Chi-square is also a very, very useful property, very, very useful distribution. And this is utilized many times when I want to check, for example, the nature of the distribution. Nature of the distribution. Is it normal? Is it exponential? Is it binomial? To be able to do that test, I must use some sort of summary that I prepare from the data. That summary, generally speaking, should be in the form of a chi-square random variable. So you've got this chi-square test, which really tests, given a particular set of data, does it conform to the Poisson distribution, or to the normal distribution, or to the uniform distribution? Whatever it is, I can check that out by doing the chi-square test. And it turns out the chi-square distribution also is found when I've got this quantity. And these are utilized whenever I'm trying to test. For example, you'll find out later on that the sample average x bar has a distribution that is normally distributed. It turns out this sample variance S square, that has a distribution that is very closely tied to the chi-square distribution. And these are useful when I'm trying to estimate the data, estimate the parameters, either sigma square or mu. I'm trying to estimate them, and I'm using data that is given to me. In one case, I can use normal distribution to guide my calculations. In the other case, I can use the chi-square distribution when it comes to the putting some limits on variance, putting some estimates on variance. Then I can use the chi-square distribution. It's useful there. So it turns out in that case, if I calculate the sample variance, it will have this distribution. It will have this distribution. And this is linked to the chi-square distribution. A very, very useful distribution. Then of course, if I compute this quantity, that will have the t distribution. Now, the t distribution is a lot like the normal distribution, like the standard normal distribution. It also rises, then it falls like this. But it's got slightly different shape. It's slightly flat as compared to the standard normal distribution. The t distribution is useful in many different ways. If I did this little transformation of my raw data, let's say my raw data was y, and its mean was mu, and its standard deviation was sigma. And if I converted all the y values into z values like this, these values, these quantities will have a normal distribution. But suppose I did not know sigma. I did not know this sigma. I did not know the population standard deviation. And in place of that, I used S. S is my sample standard deviation. If I use this, then I get a new quantity. This quantity conforms to the t distribution. So there is a difference now. I'm going away from the z distribution or the z distribution to a t distribution. And again, I've got tables for the z distribution. I've also got tables for the t distribution. And again, I can do my probability calculations because I know these distributions very well. The t distribution, there is just one difference. The z distribution does not have any degrees of freedom consideration. But the t distribution will require you to figure out how many data points you started with. And it will ask you for the degrees of freedom because it uses this quantity called S, and S obviously has a degrees of freedom. S will have a degrees of freedom. S has a degrees of freedom of n minus 1, and T will appropriately pick up the same degrees of freedom there. Finding probabilities by counting events, how do I do that? I could do that by doing permutation calculations, which is like this. Permutation is important when you're worried about the sequence. If you're worried about the sequence, like head, tail, and so on, if you're worried about the sequence, red, blue, green, if you're worried about the sequence, then you should be using permutation as your calculation basis. If in the other situation, when you are really worried about counting the number of reds and the number of blues and the number of blacks, all you really care is I want to know how many reds are there, how many blacks are there. You'll be using combination. And the formula changes, the formula becomes the formula that is shown on the thing there. Why are these calculations important, the permutation calculations, so on? Because many times when I'm trying to calculate probabilities, I will be using either a permutation basis or a combination basis to be able to do it. The simplest case, of course, is the uniform distribution, in which case I have a discrete random variable which can take values from 1 to n, and because it's uniform, the probabilities are the same for finding the values either 1 or 2 or 3 or whatever it is, and the probability of finding any one digit to be the realization or the actual number is 1 over n. That is the uniform distribution. You could also have a continuous version of the same distribution, in which case you'll have the value of f remaining the same going from one to the other end. Frequency distribution, these can be plotted very easily, these can be calculated very easily. If I have frequency data given to me, and which in some cases is quite possible, I can construct a histogram, and in some cases I would like to work out the probabilities. And for that I really have to divide the total number of frequencies, total frequencies by these individual frequencies, and I'll end up with a frequency for this, a probability for this, a probability for this, and so on and so forth. That is the likelihood of finding my random variable in this range or this range or this range and so on. That I could do just by dividing each quantity by the appropriate count of the total count of the thing. That could be done. It's something fairly simple and easy to do. It won't be that difficult. And similarly, I can work out the cumulative frequency also. This you look up, if you look up any textbook on statistics or probability, they'll give you these ideas. The Bernoulli distribution turns out to be the coin tossing situation. Remember, we tossed a coin. The distribution of coin toss, or the outcomes of the coin toss, the distribution of that comes out by the Bernoulli distribution. In the case of the Bernoulli distribution, we call the chance of success to be p. In coin toss, the value of p turns out to be approximately 0.5. That's the only difference. So coin toss is certainly not a very general situation. It's a very specific situation when my coin is balanced, and when I flip it randomly, and when I see the data, when I see the outcome of it, the outcome turns out to be precisely either head or tail, and there is nothing in between, and the chance of either finding a head or finding a tail, that turns out to be 0.5 in each case. In the Bernoulli case, of course, I have the chance of a success to be p, and I define the random variable to be having value 1 with probability p and value 0 with probability p, probability 1 minus p. 1 minus p is sometimes also written as q. So I have a chance of p or chance of q. The probability of finding either 0 or 1, that is given by this little formula, and this formula comes from the Bernoulli distribution. And the expected value for the Bernoulli random variable, which can only have a value of 1 or 0, that turns out to be p, and the variance turns out to be p times 1 minus p, or p times q. The binomial distribution is an extension of the Bernoulli distribution. What we are doing there is, we are tossing the coin not only once, but we are tossing it n number of times, and we are counting the number of heads So if you look at the Bernoulli distribution, I am actually writing down the probability of finding k successes in n trials. So I toss the coin n number of times and I count the number of heads. This distribution, the number of finding the number of heads, if that is equal to k, and if I have tossed n times, then the probability of that, probability of finding k heads in n trials, that will be given by this formula. Pk is n choose k, p raised to r k and 1 minus p raised to r n minus k. This is the chance of my finding tails, and this is the chance of my finding k heads. And this is the different ways I can construct k different heads out of n. The first k could be heads or any one of them counting to the total of there being k heads in n trials. That also could be a count of k then, or k could be just the last k pieces, last k tosses, those also could be k. So there are various ways I could generate k successes or k heads in n trials. That is why I've got this combination. I've got this combination part here. This term actually takes care of those possibilities there. And the binomial formula, again I am giving you the same binomial formula here again. This gives you more clearly what that formula is for finding a head. And notice something here, something is very important and very interesting. Under certain conditions, can you think of what this shape is now resembling? I started with some shape and I started going to higher and higher values. Look at the shape of the distribution. What does this remind you of? Well, it reminds me of the normal distribution. It turns out in some cases, the normal distribution turns out to be a pretty decent approximation for the binomial distribution. So if you get tired of calculating all the probabilities for finding head and tail and so on, using the binomial formula, just use the approximate normal formula. You'll use the same mean, which is like NP, and you'll use the same variance, sigma square. In this case, it will be equal to NPQ, and then end up with the same, pretty well the same probabilities that you will calculate by calculating the binomial probability quantity, which is like probability of finding k successes in n trials. You could work that out using the normal distribution also. Then there is this distribution called the Poisson distribution, which is also very useful in statistics. How do we use this? It turns out if we take that quantity p, remember the quantity p that we had in the binomial distribution? Suppose this quantity p became smaller and smaller, which is like if p is the fraction defective, fraction of items defective in a lot, and if this p becomes smaller and smaller, quality is obviously improving. And then suppose I want to set up a system whereby I'll be controlling quality by monitoring the number of defectives found in a sample of size n that I collect. In that case, I need not really use even the binomial distribution. I can use the Poisson distribution, which has got a simpler formula, and in many books you'll find this actually given as a table to you. The difference between the use of the Poisson distribution and the binomial distribution is this. In the binomial case, you need the size of the sample, n. In using the Poisson formula, you don't need that. So you can get very close to what we had before. You can get more or less the same numbers in terms of probability estimates using the Poisson distribution. Take a look at the Poisson distribution when it comes to shape of the distribution. Oh my God, again, the last distribution begins to resemble the normal distribution. And let me show you something else that is very interesting with the normal distribution, with the Poisson distribution. In the Poisson case, the expected value is sigma, and variance is expected value is lambda, and also the variance is lambda. So in fact, for the Poisson distribution, it's one of the few distributions which has same variance as the mean. Its mean and the variance, they are numerically the same. If I have this, I can go out and I can use the normal distribution because I have an estimate of the normal, of the mean, which is lambda, and also I have an estimate of the variance, which is again lambda. From variance, sigma square, I can estimate sigma, which is basically square root of lambda. For mean, I've already got lambda. So in this case, if I have to work out a normal distribution approximation with a Poisson distribution, I'll use a mean of lambda and I'll use a standard deviation of square root of mean. and I'll be able to use the normal tables now. That's like a big jump in terms of efficiency. Now let's bring the normal distribution in place. We have only talked about the normal distribution. It's got actually a very wide presence in the world. Almost any measurement that you do, it actually has this normal distribution. And it was found that this formula here pretty closely, resembled that bell curve. You remember the bell curve I've been drawing. I've been just drawing the bell curve all over the place. I've been drawing the bell curve like this. This shape and the formula that I show here, this formula actually describes this shape. This shape is described that F formula that I showed you in on slide 119. Slide 119. So if you look at slide 119, that slide shows you the formula, and F is the same as F has this shape. When this was found, it was found that I could really work out the mean of this. Mean is mu, and sigma is here. These two are the typical parameters of a normal distribution, which is designated by this, mu sigma square. This is basically a shorthand notation of a normal distribution, which is like this. So if this is the distribution of a random variable x, I will denote it like this. X has this distribution, which is normal, which is like this. The normal distribution has some very decent properties, and I might be able to tell you a few of them. First of all, let me tell you, if I have x distributed as normal with mean mu and variance sigma square, I cannot always find a table that will give me the probabilities for this mu and this sigma square. I may not be able to find it. Instead, what I can do is I can convert this into another distribution, which is the standard normal distribution, like this. And this distribution is called the Z distribution, which has a mean of 0 and a standard deviation sigma equal to 1. So this Z is now distributed as n 0 1. That is the distribution of Z, and the Z random variable is called the standard normal variate. I'll write this down. This is just a normal variate, and this guy is the standard normal variate. The good thing is that any of these can be converted into a standard normal variate with a simple transformation, which really says Z is equal to x minus mu by sigma. If you use this formula, any of these points from here can be converted to a correspondingly Z value here. Any value of x can be converted into this by this formula. The beauty of this is, once I've converted into this standard normal variate form, I have tables for it. So there are tables, my God, there are tables. There are tables all over for the normal distribution. And these tables provide you the CDF, and CDF is the cumulative distribution function. With that, you can find, for example, the probability of some quantity falling in this range. If you want to say there are values here a and b, and what is the probability? What is this probability p? That you can find very easily. Convert a to z value and convert b to a z value, and then just basically look up this area. Look up this area from the table, and that area and this area, they will be the same, and you will end up finding the answer for this. This is very easy. This is not very difficult. Once you do a few examples, you will be able to do this almost any time. So the normal distribution, it turns out to be this way. I've shown you, first I've shown you the density. This is the density of the normal distribution. And I've shown you the range. This is now the area. This is now this area that I showed you. This area is equal to this quantity here. This quantity here is the same as that area there. And of course, I've got my expectation, I've got my standard, I've got my variance, those are there. And it turns out if I've got two random variables, one is x1 distributed like this, x2 distributed like this, what does this guy turn out to be? It turns out to be also a random variable, which is also normal. It will have mu1 plus mu2 as its mean, and the variance will turn out to be sigma 1 square plus sigma 2 square. And that is if x1 and x2 are independent. If they are not independent, I'll end up with a covariance term. That is something that we'll study later, that we'll try to do. So the normal distribution turns out to be a very important distribution, and it's really the basis for many other tests that we have done, that are done using, for example, estimates of parameters and so on and so forth. They always come back to the normal distribution and they try to work with this. And tables are available. Remember I mentioned tables to you. These are the kind of tables that you will see once you get into textbooks. You go toward the back of the textbook, it will give you the cumulative distribution, it will give you the area, A is the area, and it will give you the corresponding value of Z. And sometimes this Z is calculated from the middle, sometimes it's calculated from the left. But the book will tell you how they are calculating these things. The book will tell you exactly how to get the correct area. So these are all available, and with this you can very easily work out the areas of your interest or the probabilities of your interest. That can be done quite easily. What are some of the other distributions that are of interest to us as quality assurance people? The normal distribution is used very heavily in control chart development, control chart work, which is like the XBAR chart and the R chart and many other charts. Very often the normal distribution is used there by invoking the central limit theorem. So that's like something where the control limits are calculated using the normal distribution assumption. Then we have another distribution called the Weibull distribution. This is a bit more complicated, and this is used when we describe the failure times. When we describe the failure times of objects, for example, the tube lights in this room, or the PC, or the hard drive of the PC, or even some object which is running on the road, or the failure time of, for example, tires on your car, for example. If you track down the failure times of these things, many of these failure times, they'll tend to appear to be Weibull distributed. And Weibull has been the basis now for modeling failure time distributions in a large variety of cases. And in reliability theory, the Weibull distribution is used a lot. So that's also a very important distribution, the Weibull distribution. It's used in reliability. Then the chi-square distribution I mentioned to you earlier, that is used in market research and also for checking independence and bunch of other stuff, distributions and so on and so forth. That is actually done quite often in statistics. When you collect data and you want to do some tests on it, many times the chi-square test is done. Then there is a very important test called the F-test, and the F-test is used alongside another little new concept called ANOVA, analysis of variance. This I am going to discuss with you later on. Much later I will be discussing a technique called design of experiments, DOE. DOE is a statistical technique which is used, and it uses a data analysis method which is called ANOVA, by which it finds out if there are multiple factors affecting a particular process, which of these factors really has a significant effect on the final process. That is done using the DOE scheme and the ANOVA data analysis procedure. Then in project management, when you've got job times, and I'm coming back to the slide here again, in project management, many times you'll ask people about when you're trying to, for example, work out the critical path network. In the critical path network, you'll require job completion times. You'll have task times, task A, task B, task C, and you'll need their completion times. If you ask subcontractors, if you ask contractors or other people, including people who do software coding or software testing, if you ask them, how much time do you think this particular job is going to do? I have some job in my hand, I'm going to give it to you, please give me the time estimate to complete this task. They will probably not be able to give you an exact time, but if you ask them, they'll say, sir, it looks like optimistically I can finish it in 2 days. Pessimistically, when things really foul up, I may take 7 days for it. But most likely I'll be able to complete it in 4 days. So here I've got 2 days, 4 days and 7 days as 3 estimates. This leads to a different distribution. That distribution is called a beta distribution. It's also called the triangular distribution. And this is used in project management, in doing PERT analysis and so on. we use the beta distribution or the triangular distribution. Then of course, in traffic studies, we already saw the Poisson distribution. We also saw the formula for it. In traffic studies, for example, for designing facilities in a hospital, or controlling traffic on the road and so on and so forth, or in queuing applications, queuing query applications, we use a distribution that is called the Poisson distribution. The Poisson distribution, and there is a very nice distribution that's used also very commonly, that is called the exponential distribution. They have a correspondence. The exponential distribution leads to time between events, which is exponentially distributed. And if you count the number of events per hour, that count turns to have Poisson distribution. So there are two things we are talking about. If you have a time axis, and if you have a time axis, and time axis goes like for say, the time axis goes like this. And what I'm doing here is, I'm counting the number of events taking place, and I've got some marks, time marks. I've got time marks like this. I've got time marks like this. In that case, suppose this is a traffic situation. I'm waiting for patients to arrive. First patient arrived there, second arrived there, third arrived there, fourth arrived there, fifth arrived there, and so on. They are arriving randomly at different times. If I look at the time between people, T1, T2, then T3, then T4, and so on. If I look at the distribution of these times, this distribution is exponential. On the other hand, if I count the number of events taking place, first event, second event, third event, fourth event, then here again 1, 2, 3. So here I had 4 events, here I had 3 events, and so on. This also is a random variable, and these will have a Poisson distribution. So there is a correspondence now between these two. There's a correspondence now between these two. And this also we exploit when we get into our quality assurance situations or other situations. We get into this. Some other places where we utilize statistics, it will be probably into drawing inferences, and that's shown in the slide here, the inferential statistics. That's like one place where we use statistics very heavily, and we use a lot of distributions like this. For example, for finding the confidence interval for a mean, we'll be using, for example, we'll be using the Z distribution, the Z distribution. If I'm trying to find the confidence interval for a variance, I'll be using the chi-square distribution. Those are like special applications where we'll be using the appropriate distributions there. Inference is basically saying something about the population based on some sample data that I've collected. That is inferencing. There is another situation when I want to say something about the process, or I want to say something about the process parameter, and I say that the value of lambda is equal to 5, or the value of lambda is not equal to 5. Lambda is the, let's say, the mean arrival rate, which is what leads to my Poisson distribution. If this is the question, I've got one hypothesis here, another hypothesis here. If I'm testing one hypothesis, which is a guess against another guess, I'll be using a principle called the tester hypothesis, which I'm going to describe to you later on. This again uses some statistical distributions, and those are now dependent on the kind of assumptions you make and the kind of test you construct. And the test could be a t-test when you're really testing the difference between two sample means, or if you're looking at the difference between two sample variances, you'll be using the chi-square test. If you're looking at the ratio of two variances, you'll be using the f-test. If you're looking at the situation when you want to check out whether two events are independent, you've collected a lot of data, you'd be using the chi-square test. That's the kind of test we'll be using. And whenever you're doing a test like this, there is the possibility of committing an error. There could be when the hypothesis is actually true, but you reject it. You say, no, it is false. It is true, but you're rejecting it. You're rejecting a good hypothesis. That's a type 1 error. And if we accept a false hypothesis, that's a type 2 error. Generally speaking, in test of hypothesis, we try to keep the error percent, the fraction of errors committed as type 1 or type 2, as low as possible. Then only we can get good sound decisions using probability theory or using the application of statistics. We actually have to count on the sizing of the sample, and also we have to look at something called the significance of the test. Significance is given by alpha in test of hypothesis, and the power of the test, which is like the power of rejecting the false hypothesis, that comes through a concept called 1 minus beta. That is also done in the same way in doing this. So we'll be looking at those as we move into this. We'll have really not much difficulty in doing that. But when I come to those application stages, as we move through this Six Sigma lecture, these Six Sigma lectures, we'll be reviewing those and we'll bring up some numerical examples also for doing them. Thank you very much, and we'll be seeing you next time in the next session. Thank you.